welcome. This is the Bau Neutron Diffraction Award that will be given this year to Arthur J. Schultz. The Bau Award is in memory of Professor Robert Bau, who was at UCLA in the chemistry department. He was also a past president of the ACA, a beloved teacher and mentor, and made major contributions to the development of single crystal neutron diffraction and application to chemical crystallography. Through applications such as transition metal hydrides, the absolute configuration of organic molecules having chiral methylene groups, and in his last years, small proteins. Our awardee, Arthur Schultz, is an emeritus scientist from Argonne National Laboratory, and after he retired, he served as a consultant at such places as the Spallation Neutron Source at Oak Ridge National Laboratory and the Lujan Neutron Scattering Center at Los Alamos National Laboratory. He has pioneered the development of time-of-flight single crystal neutron diffraction methods, the instrumentation for these studies, and also many scientific discoveries using these techniques. So join me in welcoming Professor Schultz. The title of his talk is Single Crystal Time-of-Flight Neutron Diffraction, IPNS to SNS.
Thank you for that kind introduction, and I'm really honored to be receiving this award in the memory of Bob Bau, and in particular also joining the other awardees, Tom Ketzel, Benno Schornborn, and Brian Chakamakis. And I also want to thank the ACA for selecting me for this award, and all my coworkers and colleagues over the years, their contributions. So, you know how this works. So this is an outline of my talk this afternoon. I'll begin a little bit of, provide a little bit of background about me, and then talk a little bit about the development of neutron sources, some history at Argonne, and the development of the intense pulse neutron source and the single crystal diffractometer. And then Oak Ridge, the spallation neutron source, the two instruments, MaNDI and TOPAZ, I'll talk about. And I'll end up with some research examples on transition metal hydrogen interactions. So I joined Rich Eisenberg's research group in 1969 when Rich was a professor at Brown University. And Rich was a student of Harry Gray, right here, when Gray's group was at Columbia University in New York. And they were studying transition metal coordination chemistry and realized they needed to be able to do crystal structures. And so in the summer of 1964, Eisenberg went off to Brookhaven to learn crystallography from Jim Ibers, who we've learned passed away just recently in December. And so I consider I have two academic grandfathers, Harry Gray and Jim Ibers. Well, in 1973, Rich went off to Rochester University of Rochester, and I went west to the University of Illinois in Champaign-Urbana for a postdoc with Galen Stuckey. Sorry. And in Galen's group, one of the projects was the study of one-dimensional conductors, two of which are shown here. And I knew nothing about solid-state physics. My thesis work was on molecular structure and bonding. So I got Charles Cattell's book, Introduction to Solid-State Physics, and began learning about band structure and metal insulator transitions and superconductivity. And as Xiaoping Wang mentioned this morning, the difference between solid-state physics and chemical crystallography, reciprocal space is 2 pi. Once you figure that out, it's pretty straightforward after that. So in 1976, I moved up to Argonne for a postdoc with Jack Williams, and Jack had NSF funding to support mostly chemists to obtain data and to analyze it. Now, let's see. So let me give a little history, though, of neutrons at Argonne, going back to the December 2nd, 1942. Chicago Pile 1 goes critical for the first time. And this was under the direction of Enrico Fermi. And the pile consisted of these very purified graphite bricks to moderate and slow down the neutrons so that they could then be captured by uranium-235 and produce a chain reaction. But it's interesting, they didn't really know exactly what the dangers were. So if the chain reaction couldn't be controlled by inputting cadmium rods, the last line of defense consisted of a liquid control squad. And I think they're located in this painting up here. And they stood on a platform ready to flood the pile with cadmium salt solution. And fortunately, that wasn't necessary. But we all survived that, and Chicago is still there. So shortly after that, the graphite reactor was disassembled and reassembled in Redgate Woods in Cook County Forest Preserve. And that's located about 25 miles west of the University of Chicago and a couple of miles from the current Argonne site. And at that time, there wouldn't have been any of these interstate highways you're seeing on this map, so it probably was quite a trip to get out there. And then in 1944, the first heavy water reactor was built also in the Redgate Woods. So here, the moderator now is D2O to slow down the neutrons. And there's an excellent paper by Tom Mason about in the 2013 Bragg Centennial paper, in which he notes that these were the days when scientists wore suits and ties to work. No longer the case, though. So then CP4 was actually an experimental breeder reactor that was built out in Idaho to produce electricity. And CP5, before I get there, parts of CP2 and CP3 are now buried in the Redgate Woods, and this is open to the public. So you can go hiking around, and you will run into these two markers here, and they explain what's being buried there and how dangerous it may or may not be. And whoops. So buried in this area is radioactive material, and it does warn you, it says, caution, do not dig. So they were very trustworthy in those days, I think. But anyway, that's what's there. And so now here's CP5. So CP5 was the last of the CP series, but the first and only one built on the Argonne campus. And this was a 5 megawatt heavy water D2O reactor. And a lot of science went on here. So why is neutron scattering useful? Some of the obvious things. And here's a figure from George Bacon's group. And nuclear cross-sections are similar across a periodic table. And that's shown here, whereas these are the scattering by electrons by X-rays. So we can see here that hydrogen is almost the same in the magnitude of scattering as some of the heavy elements, including uranium out here. And therefore, they can be observed in structures and other techniques. Isotopes of the same element have different cross sections. So the most famous, of course, is hydrogen, which has a negative scattering length, and deuterium has a positive scattering length. And so the HD distribution, for example, can be analyzed in materials. And neutrons are highly penetrating. Most isotopes do not absorb neutrons, which is good because our samples are usually pretty big. But this also is very helpful in designing ancillary equipment such as pressure cells and furnaces and refrigerators. And the magnetic and nuclear cross sections are comparable. So of course we can do both the nuclear structure of materials, but also magnetic structures and study of magnetic materials. So a little more history now. In the 1960s, to replace CP5, the construction of the Argonne Advanced Research Reactor began, so-called A squared R squared. And the Argonne Chemistry Division wanted to have a four-circle diffractometer, a single crystal instrument in the new reactor. And they actually recruited Selmer Peterson to come to Argonne to build the reactor. Peterson was a pioneer in single crystal neutron diffraction at Oak Ridge. And at that time in 1949, when he came to Oak Ridge to work with Henry Levy, it was thought that single crystal data might not be very useful because of secondary extinction. And those were based on calculations, so apparently, Peterson and Levy decided to actually test this. And in this paper in 1951, they say that the use of single crystal neutron reflections for crystal structure determination appears practical in many cases. And they were looking at simple salts, sodium chloride, et cetera. And they went on to do a number of structures in the next few years, including the single crystal structure of D2O ice, one of their more famous results. So what happened? A squared R squared was canceled in 1968, mainly due to budget issues. And so Selmer Peterson and Jack Williams built a four-circle instrument on the CP5 reactor. Jack was initially a postdoc at Argonne in the metallurgy division, and he was going to team up with Pete to build an instrument at A squared R squared, but instead they built it at CP5. And actually shared a beam line, so there was an instrument below this. This was up on a deck. And I don't know, let's see if we can see this. So the beam's actually coming up almost vertically. The sample would be here. Here's a BF3 detector on a 2 theta arm, and the beam stop would be up here somewhere. And this instrument was really quite nice. It ran on the Sigma 5 computer in the chemistry building about a half a mile away. And it was easy to operate, and we could see all the peaks every day. So with the cancellation of A squared R squared, Jack Carpenter, who was at the time a professor at the University of Michigan, proposed a pulse-spallation neutron source instead of trying to build another new reactor. And this is a slide from Jack, why pulse neutron sources? And well, particularly for reactor sources, experiments are intensity limited. They're much orders of magnitude less than even from a laboratory X-ray source. But neutron flux of reactors has practical limits. In particular, I keep doing that, sorry. The flux is limited by the inability to remove heat. So as Jack would say, it's really an engineering issue. Whereas pulse spallation sources promised 10 to 100-fold increase in peak thermal flux. And the reason is the heat deposition is pulsed. but the cooling is continuous. The other feature is that spallation process shown here. For each proton that hits a heavy metal target to produce neutrons, we get 20 to 30 spallation, but fission, we only get 2 to 3 for every fission reaction. And finally, there are fewer licensing and safety problems than for a pulse source relative to reactor. And so that's actually quite important. So all the new sources that are being built are spallation sources. So it was decided to try and build a spallation source, and Selmer Peterson led the design of the IPNS SCD instrument in the 1970s. And this is a photograph of the prototype instrument at CP5. So just should mention that, Pete was really a pioneer, both initially with single crystal diffraction at Oak Ridge at the graphite reactor down there, and then also with a pulse spallation neutron source, developing the time-of-flight Laue technique. And here we see a photograph. This would have been 1979, I think. And here's Peterson and his coworker, Art Reese Jr., mounting a crystal. The beam comes here, incident beam. And this is a helium-3 multi-wired detector, position-sensitive detector, which we shared with the small angle group for this experiment. And so I was working a lot with Pete at the time. We performed a proof of principle experiment in 1979, analyzing sodium chloride data. And then after Peterson retired in 1980, Ray Teller, who's here today, a student of Bob Bau, and I took over the project. And so on the left there, you see Ray Teller nailing polyethylene to the walls of the SCD hutch. And the idea was to line it with polyethylene to moderate the neutrons, and then to capture the neutrons with borax, with boron 10. In a few years, Ray would leave Argonne and then return in 2000 as the IPNS division director. And here is me up there with the mask on, filling Sears downspouts with 20 multein borax to line the inside of the hutch. Now, I should add that the reason we're doing this is that the construction crew wasn't really working on the SCD. We couldn't get them to do this work. And we wanted to be ready when IPNS turned on in October of that year of 1981. And so I had written in my notebook on April 1, 1981, called Al Knox, a project manager, we will have to fill 500 downspouts with 18,000 pounds of anhydrous borax. And we did it. And when the beam turned on, the SCD was ready to collect data. So here's a schematic diagram of the intense pulse neutron source. They start out with H- particles, which are accelerated in the LINAC here, turned around and injected into the rapid cycling synchrotron. And when they're injected, the electrons are removed by passing it through a charged graphite thin film. And so now we have protons accelerated in the RCS. And this source ran at 30 hertz. So 30 times a second, a pulse protons would come down the beam line to the neutron scattering target, which at IPNS consisted of depleted uranium. And then surrounding that are various moderators and the instruments. So down here we see the SCD. And also for the last 8 or 10 years of operation, I was instrument scientist for the high intensity powder diffractometer, which sat at the other side of the monolith here. So this is a comparison of steady state versus time of flight diffraction. So typically with a steady state reactor, one would select one wavelength of neutrons with a macromolecular crystal. And then there's a sample, and the detector would step through some 2 theta angles to collect data. And so in the Bragg equation, we're varying sine theta and lambda is a constant. And with the time of flight technique, here's the source and the sample, and the source is pulsed, so we can measure wavelength by measuring the time of flight with a fixed path length using the de Broglie equation shown here. And so with time of flight, we can fix the angle here, so it's a fixed 2 theta angle, and we're varying wavelength in the Bragg equation. So one big advantage of pulsed neutrons is that all the neutrons can be used because we can determine their wavelengths by the de Broglie equation, whereas at a reactor source, we typically select a small range of wavelengths and all the other neutrons are not used. So this shows what's the time of flight Laue technique in the reciprocal space. And basically during each pulse, right at the beginning of the pulse, the neutrons emerge, all the neutrons emerge, and then they sort themselves out by velocity. So the first neutrons to actually hit the sample have the shortest wavelength and the largest A-volt sphere. So that would be the large sphere here. And then towards the end of the pulse, the slower neutrons have the longer wavelengths, and they would have this A-volt sphere. And everything in between these 2 spheres can be sampled and measured. And so if there's a point detector sitting out here at 90 degrees, we can actually sample this whole lattice line here. And with an area detector out here, we can sample a solid volume of reciprocal space during each pulse. And so if we had an area detector, and here's what looks like a peak on the detector, but it's we've got a third dimension. And so here we see that one peak actually can be resolved into 8 or 10 peaks. And so that's one of the really powerful things. And we can also map the data using this program into a 3-dimensional reciprocal space. This is a program called ISO, a suite of programs, Integrated Spectral Analysis Workbench. It was mostly written in collaboration with Dennis and Ruth Mickelson from the University of Wisconsin. And in this case, the data we're looking at is a zinc manganese oxide from William Ratcliffe. And if we step through the data or rotate the 3D data, we see these very clearly, see these rods of intensity, and they're due to two-dimensional magnetic ordering at low temperature. But this kind of visualization makes this technique really useful, as you can see. So here's the drawing and a photograph of the first IPNS single crystal diffractometer. The sample is here, and the incident neutrons come in this direction. Actually, we moved the instrument from that hutch to a different beam line, and now we're at 9.5 meters from the liquid methane moderator. And then at 90 degrees, there's a 30 by 30 centimeter active area detector. And here's a photograph. This is a Chi circle. This is the evacuated sample chamber. This is a displex refrigerator. And we can rotate in Chi from 180 to 90 and rotate a full 360 around phi. The detector is back under shielding back there, and this is a get lost tube. So at IPNS, we really pioneered the development of the position-sensitive Anger neutron detector. named after Hal Anger, who was an electronics engineer and developed this for gamma ray medical imaging. And the power of this detector is that even though this array of photomultiplier tubes, 7x7 array, each tube being about 50 millimeters on an edge, by determining the center of mass or the centroid of each neutron event, we get a resolution of 3.5 millimeters with this detector. So the signals from the photomultiplier tubes are scaled by their row and column, and that's how we get the centroid. So the advantages of the Anger neutron detectors relative to helium-3 detectors include higher efficiency, the lot more lithium-6 in even a little bit of scintillator glass versus a couple atmospheres in a gas-filled detector. Minimal parallax, the scintillator material is only around 2 millimeters thick down here. And this is a scintillator glass, would sit in front of the photomultiplier tubes. It's more compact, less dead space around the detector for tiling several detectors around the sample, easier to construct and less expensive. So it has a number of advantages, and particularly for getting to high Q, high resolution, small molecules, this detector still has very good efficiency, even at such, let's say, half an angstrom neutrons. So in about 2001, the SNS came to us and to develop what I call the second generation Anger detector. And so here we see a schematic of the detectors and a photograph. So this is now a 7x7 array of 1-inch square tubes. And the major advance here is now the detector puts out a digital signal rather than analog. And that allows the digital data to be fit to a light spread function, typically a Gaussian, which turns out to be more accurate than doing the centroid calculation. And so now the resolution is down to 1.75 millimeters. These detectors, as you can see, are more compact, and there's better linearity and accuracy near the edges, again, because we can fit the light spread function. And this detector was mostly designed and built by Pat DeLergio at Argonne. And just currently, the current generation of Anger detectors at Oak Ridge, one of them is shown here, Anger detectors. And so this is the front end of the detector where the scintillator is. And now there's a 3x3 array of roughly 2-inch square tubes again, but these are now segmented multi-cathode photomultiplier tubes. And there's an 8x8 array, so each of these multi-cathodes, the spacing is about 6 millimeters. And so now the resolution is 1.2 millimeters, so it keeps getting better. And there are about close to 100 of these detectors currently operating on the SNS. Well, in 1980, let me get my dates right. In 2008, okay, a little bit off there. In 2008, in January of 2008, IPNS was shut down. And that July, we moved, with the help of Rich Vitt, my colleague at Argonne, we moved the instrument to Los Alamos and set it up on a beamline with the help of Heinz Nakati, a professor at New Mexico State University, and 2 of his grad students shown here. And we got it working down there, and it ran for a couple of years, a couple more years. So in addition to the many people inside of Argonne who worked on various aspects of the SCD development, there were a lot of people from outside who wanted to help and kind of joined in on various aspects. And so here's a partial list of some of the people and what their contributions were to the software development, mostly. So in around 2000, construction began on the spallation neutron source, the SNS. And this is a current photograph. And it starts out with the LINAC, and then the H- particles are injected into the accumulator ring here, where the electrons are stripped off. And then this source runs at 60 hertz, and it's using flowing mercury target as a target to produce neutrons. And in addition, there's the offices and labs and a nano center. And while construction was going on, so was development of instruments. And here we see Christina Hoffman and Xiaopeng Wang, the instrument scientists. And this is the detector array tank. And you can mount detectors on these aluminum windows. And it's also called the Hoffman teapot design, because Christina initially designed this by attaching Post-it notes to her teapot. And anyway, there you see it. And here it is now mounted on the beamline at the SNS. Here's the incident neutrons, the DAT, detector array tank. Detectors are mounted. They look precarious, but they're pretty stable, it turns out. And the crystal is mounted on the goniostat here, which is on a little elevator, so we can move it up to here, mount a crystal, and move it back down into the tank. And this was designed by Crystal Logic company, Chuck Strauss. And there's also a video microscope here, so we can align the crystal remotely on the computer with the computer. And here you see what some of the data looks like. This is, I think, with 18 detectors and like a wavelength bandwidth of about 0.5 to 1 angstroms. And this view here is using another software package called Mantid, which is a collaboration mainly with the SNS and the ISIS in the UK. So these are the Bragg peaks we're seeing here. So of course the next step is integration, which I'll talk about in a second. But initially, then once the peaks are integrated, they need to be reduced. And Christina Hoffman this afternoon will talk about that in the session on opening the black box. We'll see what's in there. So one of the analyses we did was to test and analyze what's the best way to integrate the Bragg peaks. And the major finding was that we get much better results if we map the data into reciprocal space and then integrate, rather than trying to integrate in detector space on the detector themselves. And so then in reciprocal space, I think we get nicer shaped peaks, so it's easier to integrate. And here we see for a spherical integration, this would be the background, the gray, and this would be the peak here. And this slice is kind of normal to the HKL vector, and this is along the HKL vector. And we can also fit ellipsoids to the peaks and integrate that way, which is, I think, typically what they do now. But we also found that we could do one-dimensional profile fitting. And so what we've done here is fit this cylinder here, center it on the peak, and align the cylinder axis with the HKL vector. And then all the neutron events are added to the profile along the axis here to give a peak that might look like this, the solid line. And then we can fit that to a Gaussian convoluted with an exponential term. And so here's just the Gaussian, doesn't give good fit here, but then exponential fall off, we'll get really nice fits. And then using the calculated integrated intensity under the peak actually gives better results than peak minus background integration, either one-dimensional or three-dimensional, whatever. So in certain cases, this actually gives the best results. So then also back in around 2001, my colleague Papanand Thiagarajan, I always have trouble with that, also known just as Thiaga, came into my office and said the SNS wanted to know if, well, they had an empty beam line and they wanted to know if it could be used for macromolecular neutron diffraction. And the real issue with that was that the beam line looked at a decoupled hydrogen moderator. So this is a moderator, so the liquid hydrogen in these moderators is about 1 liter. And if you align it with cadmium, except of course in the direction where the beam goes, the sample, then you decouple it from the beryllium scatterer that's surrounding the moderator to scatter neutrons back into the moderator. And it's also poisoned with gadolinium, with the gadolinium foil. And what this does is reduces the amount of time that neutrons can bounce around in the moderator. And so you get very good time resolution. The thing is, and that's shown here. So the red curve shown here is the calculated flux for a decoupled moderator. This is the coupled moderator, which is coupled to the beryllium reflector, and neutrons bounce around a lot. So there's a lot more flux, but most of it's going into background. And also the resolution is just not good if you needed to resolve another peak right next to it. So compared to the coupled moderator, there is a loss of intensity, but there's much better resolution and lower flux, but better signal to noise. And so the end result is, for any sample, the beam time will be shorter. We can measure smaller samples with bigger unit cells. And so the conclusion was that beam line would be excellent for doing macromolecular diffraction. And we did a number of conferences, and in 2013, the first experiments were performed. So now I'll talk a little bit about some, how am I doing for time here? Good. Major research topics studied on the SCD and TOPAZ, very briefly. One area of research was organic superconductors. Jack Williams' group was very active in this area, and they produced several new superconductors, and we studied some of them with neutrons on the IPNS SCD. The Jahn-Teller switch and Tutton salts, Charlie Simmons came to do an experiment, and he wanted to test to see what happens with the Jahn-Teller distortion in this hexa-aqua-copper complex, they're called Tutton salts. And we knew that there was a difference between hydrogen and deuterium. And when he applied pressure to the deuterated salt, it actually switched. And so now it's isostructural with the hydrogen. And this is a cooperative event in which the hydrogen bonding network, all the copper switch at once. This was totally unexpected. And we actually had to use Multan to initially figure out what was going on. But that led to a lot of new experiments with Charlie and others. Another area of research is currently is ferroelectrics containing hydrogen, and these are data for KDP, and Xiaoping talked about that this morning. And here we see the population of the different domains throughout the hysteresis loop where we vary the field, and this is a polarization. And so what's called event data, where each neutron, individual neutron, is stamped with its time, a wall clock time. we can then reanalyze the data and do these what's called time filtering. We've done a number of transition metal hydride complexes. This is one from Al Cotton's group. It's a zirconium cluster, well, 6 zirconium atoms and hydrogen atoms sitting on the face of the octahedron here. And the results agreed very well with calculations in this case. And finally, I'll talk about some transition metal hydrogen interactions involving XH metal bonds and molecular dihydrogen complexes. So this manganese molecule from Maurice Brookhart's laboratory was the first experiment on the IPNS SCD. So we collected data, but then the structure wouldn't refine using the X-ray model. And this was we're very anxious about this. Teller and me went through all our code to see if we made any mistakes. And we asked Mark Bino to try to solve the structure by direct methods. And he was able to do that. And we discovered that we had indexed the peaks with a non-standard unit cell, which metrically looks similar to the standard one. Anyway, once we corrected for that, the refinement went normally, and it was a very good refinement. So that worked out well in the end. So the molecule is actually an intermediate between a metal allele, shown here, and a metal diene hydride complex, shown here. So here's the hydride. So essentially, we're extracting an H atom from a CH3 group and forming a metal hydride. The carbon, hydrogen, and manganese interaction is characterized by a very long CH distance of 1.19 angstroms compared to a normal value of 1.09. And with the 2 electrons in the CH bond, we have the formation of a 2-electron, 3-center CH manganese bond, which allows the complex to then achieve an 18-electron closed shell configuration, which gives it its stability. That's why we can see the intermediate here. So just some history. In the early 1970s, Trofimenko and Cotton first proposed 3-center 2-electron bonds in these paraxylene borate complexes shown here, in which there's this BH molybdenum interaction. And with the 2 electrons, again, in this, the molecule then achieves a closed shell configuration, similar to that manganese molecule. So I think Glenn Yap met Tom at some meeting, and he proposed that we look at a series of complexes with neutrons, because even though back in the 70s they proposed these 3-center 2-electron bonds, there had only been X-ray data collected. And so a series of molecules was synthesized in their Delaware laboratory, containing different substituents on the paraxylene ligand. So phenyl groups, methyl groups, in one case a halide. And we collected data on 4 molecules. The analysis was done by John Cowan and Paula Piccoli. And one of the findings was that a closer approach of H1A to molybdenum to the metal, that is, as this bond gets shorter, this bond gets longer. And that's shown here in this plot. And so this is similar to, or analogous to, what we see in other hydride complexes. The transhydride structural effect is observed in these compounds. Another type of CH metal interaction is observed in these 2 tantalum-alkylidene complexes. And these molecules were from Richard Schrock's laboratory at MIT. And these are tantalum complexes. This molecule is actually a dimer. We're only seeing half the molecule. But normally, if you consider that this is a carbene, then you would expect that all the angles around the carbon are 120 degrees, because it would have sp squared hybridization. That's not the case. So there's some interaction here, the hydrogen with the metal. And this angle here is now, I can't read it here, but it looks like 85 degrees. And this angle is down here is 162 degrees. So it's very far from being 120. And the same is true in this molecule, this shown here. So one way of understanding a bonding is just from this article by Robert Crabtree, this review article in Angewandte Chemie. So he's proposing that he's calling these transition metal sigma bonds. And here the sigma bond refers to the XY sigma bond, which then is a dative bond. It donates electrons to an empty metal orbital. In addition, Crabtree noted that then we could have pi back bonding from a filled metal orbital into the XH sigma star antibonding orbital, which will weaken that bond and possibly produce oxidative addition. I should add that the tungsten and molybdenum analogs of these molecules are catalysts for olefin metathesis, where we exchange groups on two olefins. And Schrock shared the Nobel Prize in 2005 for those catalysts. So the special case where X is equal to hydrogen is a dihydrogen complex. And in 1984, the first dihydrogen complex was, a stable complex was prepared by Greg Kubis at Los Alamos. And they actually collected data with Phil Vergamini on their single crystal instrument at the Lujan Center, what's now called. And anyway, so here we see a series a few years later with that we did with Greg Girolami at the University of Illinois on a series of osmium complexes. And here, where this ligand is triphenylphosphine, we have a rather long HH distance of 1.01 angstroms, so already pretty long. A typical, in free dihydrogen, the HH distance is about 0.8. If we replace triphenylphosphine with triphenylarsine, the distance is now 1.08. And then finally, with tricyclohexylphosphamine, we're getting to really bulky ligand here. The distance is 1.31, but not only that, the dihydrogen has rotated by 90 degrees. So here it's in the plane of the centroid, the metal, and the ligand, where here it's perpendicular. So actually, Mike Hall and his student Webster did calculations. And one way of understanding this is based on some calculations from Roald Hoffman and coworkers. And they were analyzing carbene ligand to a transition metal, the bonding of that. And the dihydrogen, and here we see the dihydrogen antibonding orbitals plays the role of the empty metal pi acceptor orbital on the carbene ligand. So that's this here. So that's basically looks like the sigma star antibonding orbital in the dihydrogen. And that rotates by 90 degrees if we have some kind of bulky ligands here that reduces this angle. And so now by flipping 90 degrees, the dihydrogen can overlap with the DXY orbital. And so we get a lot of electron density into the antibonding orbital, giving us a long 1.3 angstrom bond length, and the reason for this rotating. There continues to be a lot of interest in dihydrogen complexes and possibly with metal organic framework materials for hydrogen storage. The advantage is that we actually never break the HH bond, so it's easier to form the bond and then release the hydrogen. So currently, the spallation neutron source is proposing to build a second target station, and it would be right next to the first one. So here's the current target station. So this would take some of the proton, every fourth pulse of protons, and it would be a 15 hertz source. And one of the instruments being designed and proposed to be on the second target station is called Pioneer. And it's proposed that possibly this will allow us to collect data on a crystal that's 0.001 cubic millimeters in volume, which is the size of a typical X-ray crystal. Bob Bell would have loved this. This was one of his dreams. And so we're hoping that will happen in the near future. Well, Bob was actually the chair. I haven't mentioned that yet. He was chair of the TOPAZ Instrument Development Team. And this is a meeting in 2006 at the SNS. You'll recognize a lot of the people here. He had injured his foot, so his wife Margaret came with him to help him get around. So once again, I want to thank the ACA for this award, and I want to thank all my coworkers and colleagues for helping me. And it turned out this was a family project preparing this talk, so I need to thank my wife Ruth and our son Michael for all the help they provided in preparing this talk with me. Thank you.
Well, great talk, Art. Tom Ketzel, my name, sorry. Second time I forgot that. As you say, Bob would have been absolutely thrilled with this success projected that we could finally achieve our dream of collecting on an X-ray sized crystal. And I'm just wondering if, what would the increase in flux be actually on this projected instrument Pioneer compared with what we started out with 30 years ago on the first generation machines?
Yeah, right. Well, I can tell you that SNS, the first target station, it's 2 orders of magnitude more intense than we had at IPNS. So, you know, they've been doing crystals that are 50 to 100 times smaller than we could have at IPNS. So the big advantage of the second target station will be in brightness. So they'll be looking at just a 3 centimeter moderator, whereas currently we're looking at a 10 by 12 centimeter moderator. They'll be maybe 60 meters versus 30 meters from the source. Yeah, and they'll probably looking for possibly using KB mirrors to focus the beam. So the idea is get all the neutrons on this tiny sample, otherwise they're not helpful.
Thank you.
Please join me in thanking Professor Schultz for his wonderful talk.